The last class we have calculated our swing equation during the fault for during a fault at a short circuit fault at this bus, and we have seen that during the fault that PE1 was 0 because the fault was near to the bus bar 4. Okay, so that's why the electrical power goes to 0, but we have the electrical power at PE2 was not equal to 0. Okay, so here we will calculate calculate the circuit breaker time or critical clearing time, or this time will be given to your circuit breaker to operate to clear the fault. Okay, so this is my circuit breaker, and this circuit breaker needs to be given some time, and how you can give this time for the calculation. So this here we have seen that p is 0 is 0. Okay, for our if I want to decide the rate the timing of the circuit breaker here, uh, using this equation that our electrical power at G1 is 0, write your swing equation. So I have left with d square delta upon dt square, and that was equal to 180 f by h1. Okay, and h1 multiplied by ps minus pe1. Okay, so this is my equation, swing equation. Now, as you know, pe1 equal to 0. So pe1 equal to 0, if you put it, so you will get d square delta upon dt square 180 f upon h1 ps. Now integrate with respect to integrate with respect to time. Okay, so if you integrate with respect to time, you do it dt here, you do it dt here, and integrate this equation. So what you will get, your 1 dt cancel off, so you will get d by delta upon dt, and you will get 180 f ps upon h1. Okay, and if you are integrating, so it will be t. Okay, again integrate with respect to delta dt, again integrate with respect to dt again. So here again, if you integrate with respect to dt both sides, so you will get delta is equal to, so this dt get cancelled, so you will get delta is equal to 180 f by h1 ps t square upon 2. So dt t square upon 2 plus as it is an indefinite integral, so there will be a constant. Okay, so this is an you can say this is a constant, this is an initial condition, whatever you want to say you can say it. Okay, so how we will find out the initial condition? So initial condition, when t tends to critical clearing angle tc, delta tends to critical clearing time Tc, delta tends to critical clearing time delta C. Okay, so at initial condition, what happens? Initial condition delta goes to delta 0. So this is the initial point that you are operating, initial angle which you are calculating. So you can put here t equal to 0 for initial condition, t equal to 0, delta equal to, if you put the value t equal to 0, so delta will be equal to delta 0. So finally you will get delta is equal to 180 f upon h1 t ps tc square upon 2 plus delta 0, right? So this is my equation. So from here, if I want to calculate the TC, what you will get, just summarize it. So you can get this value of TC So then you can make it like this: del minus del 0 is equal to 180. So I'm giving it a bit shortcut. So 2 upon 180, 2 upon h1. Okay, so I'm also putting it like this. So it can be written as 2h1 upon 180 fps. Okay, and tc. So tc, a square root will become here, right? So this is the critical clearing angle or critical clearing time that you need to give it to the this circuit breaker to operate, and this is how you can calculate that critical clearing time also. Now there is some probability that how we will if PE is not zero, PE is not zero, then how will you will calculate? Now you have seen here when PE2 was not equal to zero, so you got some equation that was your in the previous class you have calculated PS minus some quantity, yes, cos delta, like that you got cos delta minus cos delta 0, like that quantity you got. So I didn't remember that, but this is the equation which you have got. Now for a particular delta, if you are operating at a particular delta, put the value, your this quantity will change here. Okay, so now so that is your accelerating power. So you can calculate TC is equal to 180. Sorry, you can calculate like this: root under 2h1 h1 upon 180, or h2, you can say h2 upon 180 f. Now this will be PS minus PE2. Okay, so here PE2 is not 0, put it here, and it will be delta minus del 0. Okay, so this is how you can calculate your equation, and it will be feasible for you to calculate the circuit breaker timings. Okay, so this is if given the different values of your delta, you can calculate PE2, put the value P2 here, you can calculate the timings of your circuit breaker, and that will determine your operation. Okay, so till here I have completed your unit number 3, and we'll move on to unit number 5, that is your HVDC transmission. Okay, so thank you. So next topic is HVDC converter and rectification. HVDC converter and inverter ends. Okay, so this part is mostly dependent on one of your subject, that is your power electronics. Okay, so how you have learned your power electronics, that will determine your this part. And basically, if you say particularly first half, that will be concerned about your three-phase rectification. Okay, three-phase rectification, and then we'll go for the three-phase invertification, you can say. Now here, this is the first inverter you have read about in a three-phase supply. So before that, we'll understand the pulse, how we can say what are the pulse. Now once if you have seen that there is an AC supply, and you put one diode, and there is a load, so this, how will you get the output pulses? You will get this type of pulses. Okay, and then you will not get any pulse, and then you will not so for one 2 pi cycle you are getting one pulse, so this is called as one pulse. Okay, one pulse converter. Similarly, when there was a bridge type converter, bridge end, single phase bridge end converter. So how you are getting the convert outputs of your DC supply? So this is your, now after getting this, you will get like this type of output. Okay, now this is the output you are getting from your single phase full bridge converter. Okay, and this is for a 2 pi cycle you are getting 2 pulses. Okay, so this is your 2 pulse converter. Okay, similarly, when your three phase supply was there, this was your R, this was Y, and this was B. So your R, Y, B phases are their phase voltages, and you are getting your output was like this, right? So this is your R0, Y0, B0, right? B0, and then again R0. It goes on. So it conducts from some period. Okay, what is that period? So that period was, I think, pi by 3, 60 degree. After 60 degree it was operating like that. So you are getting, for a first 2 pi cycle, if you see, you are getting uh, 3 pulses. So this is called as 3 pulse converter, right? 3 pulse converter. So here again, this is a full bridge, 3 phase full bridge converter. Now here if you see, your output was actually your line to line voltage. So this is A, this is B, this is C. So when your 1 and 6 conducts, 1 and 6 conducts, you are getting VAB. Okay, VAB as the output. Okay, similarly, when your 1 and 2 conducts, so you are getting VAC. So you are getting actually a line voltage. Here you are getting a phase voltage this side. So for this type of converter, for 2 pi cycle, you are getting 6 pulses. Okay, so 6 pulses. So this was your VAB, VCA, and so on. Okay, so this was your 6 pulse converter. 6 pulse converter. Now, as you can see here, there are number of pulses. For a 2 pulse converter, a single pulse converter, 2 pulse converter, 3 pulse converter, and 6 pulse converter. We have talked about 12 pulse converter also. So 12 pulse converter, one more bridge if you attach like this here at the bottom part, and make it a ground, connect one more bridge here, okay, like this, and operate. So this will be your positive link, this will be your negative link, and this will be your negative link, and this will be your grounding. So the total converter from here to here is your 12 pulse converter, right? This is a 12 pulse converter, 6 pulse up, 6 pulse down, that will be your 12 pulse converter. Okay, so this is how we are transferring energy in your converter side, from converter side. So once this is your three phase transformer. Initially this is an AC supply. If you are connecting an AC supply here, and you are stepping down or stepping up using a star delta transformer, and then you are transferring it. So you can use, your number of converters are there. Basically for a three phase supply, we are focused on either 3 pulse converter, 6 pulse converter, or 12 pulse converter, because these three converter resembles more like a DC supply. More like a DC supply means your DC supply is actually a straight line. Now if you see here, for a single pulse converter, if you draw the straight line, it has a gapping here. Okay. Similarly, for a two pulse supply, the number of pulses is very less. So it resembles less like a DC supply. Three-phase supply is resemble somewhat like, because there is less number of fluctuations. Now for a six pulse, if you see, it is most likely to be a DC supply. Again, if you increase the number of pulses, 12 pulse means more number, small pulses. Okay, so this is mostly a comparatively directly, you can say that very less amount of from the waveform, there is very less amount of part that is not resembling like a DC. Most of the thing is a DC supply. So terming the resemblance, we can say that that term is called as ripple. Okay, ripple is the same term. So we can say that for as you increase the number of pulses, as the number of pulses increases, the ripple decreases. Okay, ripple decreases, that means you are getting more DC. Okay, more DC part. So that's why the difference is. See, one more thing, that when you are converting DC to AC, you are getting harmonics. Okay, and when you are converting AC to DC, you are getting a ripple. So there is a difference between harmonics and ripple. Never use ripple in place of harmonics, or harmonics in place of ripple. So this is the major part. Okay, so I hope you might have cleared about the pulses. Next we will do the equation part. Okay. uh, For our three-phase supply or three-phase HVDC transmission uses three pulse converter or six pulse converter, and a max generally it uses 12 pulse converter, but these are the basics, or these are the base converter that are used for a 12 pulse converter. Okay, so I'm generalizing it as an n pulse, n, where n refers to the number of pulses. Okay, so if I am writing it like this, for three pulse converter, your degree, that this is your phase voltages, VAO, VBO, VCO. Okay, and this starts from 30° and it ends at 150°. Okay, that means for 180° cycle, or sorry, for a 360° cycle, for a 360° cycle, you will get three pulses. Okay, you will get three pulses. So one pulse will be of 120°, right? Similarly, for a 360° cycle, you are getting six pulses. For one pulse cycle, you will get 60°. Okay, so and this will go on. So here it is your 30°, so the difference is 120° for a three pulse. For for six pulse, the difference will be 60°. Okay, so what I am writing it like this. So our initial angle, that it varies from 30° and it goes to 150°. Okay, so I am writing it like this, that is your pi by 2. So pi by 2 minus, that is 90 minus, how much? 90 we have to subtract so that I can get 30°. So I can put it like this, pi by 3. So if you subtract this thing, you will get 30°. Similarly, pi by 2 minus pi by 3, pi by 2 plus. So I am generalizing. Similarly, for a 6 pulse converter, that will operate from, I think it will operate from 60 to 120°. Okay, so so this initial point will be a 60. So I am writing it like this, pi by 2 minus pi by 6. Okay, pi by 2 minus pi by 6 and it goes to pi by 2 minus plus pi by 2 plus pi by 6. Okay, so this is how the shape changes, the limit changes. So what I can generalize is that my for any pulse, for n pulse converter, your pulse will change from the upper limit, the lower limit will be pi by 2 minus pi by n, and it goes to pi by 2 minus pi by plus pi by n. So this is the limit for an n pulse converter. Okay, for an n pulse converter, the limit, lower limit is pi by 2 minus n, and it goes to pi by 2 plus n. Okay, so if I want to, so this is a general way. So if I want to calculate the RMS or average value of the current, as you can see here, all the currents are in sinusoidal form. You can use sine or cosine, whatever you want. So if I want to have the average value, that is your V naught. So V naught can be said as 1 upon time period integration 0 to time period, or okay, so 0 to time period, uh, whatever the waveform which you are getting, waveform is your sine omega t. So sine theta I am putting it, and d theta. Okay, so I am not putting it omega t, it will be complex for you, so that's why I am putting it easy. So what I can say, 1 upon time period is 1 upon t. So total time period is 2 pi, but the number of pulse will be n. Okay, so this is the time period, and it goes from, so I'll not put 0 because my initial limit is, my initial waveform starts from pi by 2 minus pi by n, and it goes to pi by 2 plus pi by n. Okay, and it the waveform will be Vm sine theta d theta. Okay, so if you integrate this, so I will discuss, actually I am not interested in drawing the waveforms and then I'll calculate it, because these things have most probably have been done in your power electronics part. So I'm not interested in doing that. I'll do the rest of the calculation. So I can put it like this, n upon 2 pi. So I'm putting it Vm outside. So sine omega t will be your minus cos theta, and it goes from pi by 2 minus pi by n. Okay, and pi by 2 plus pi by n, put it like this. So n into Vm upon 2 pi. So I'm putting it like this, cos pi by 2 minus pi by n minus cos pi by 2 plus pi by n. Okay, because there is a minus sign, so I am putting this upper value last and the lower value up, that's why minus sign. So this using your simplification term, I can directly put it like this, that is your sine pi by 2 pi by n, and this will be your plus sine pi by n. Okay, this is sine pi, this will be your sine pi by n, this will be your plus sine minus sine pi by n, and minus minus plus, so that should be given. So v naught I can write it like this, so v naught I can write it Vm upon pi by n sine pi by n. Okay, so this is the final value which you are going to get. And now if you change the number of pulses, if you get n equal to 3, put n equal to 3, you will get V naught is equal to 0.83 Vm. Similarly, I put n equal to 6, you will get V naught is equal to 0.95 Vm. Go and check with what you will get, Vn is equal to 12. So check it the value. What if you see here the values, it the output voltage or output DC voltage is increasing. Okay, if you increase the number of pulses, the output uh, output DC voltage increases. It was 0.83 times or 83 percent of your maximum value. It is 95% of your maximum value. Okay, so that is the advantage of this waveform. Now, if you see the current waveform, if you see, it is a square shaped waveform. Okay, so I will tell you the disadvantage of this waveform, because that's why that hampered our transformer. So that's why we have changed from 3 pulse to 6 pulse. So why the disadvantage of this square wave made us use either the minimum criteria to use 6 pulse or 12 pulse or 24 pulse. We can't use, means you can use converter above 3 pulse but not 3 pulse. You can't use converter that of 3 pulse converter. Okay, it made us limited because of this waveform. We will discuss more on that in the next class. Okay, thank you.